Hi everyone, this is Ramya. My project title is Wind Power Inverter DC Bus Voltage Control based on First-Order LADRC. These are my project associates and this project is done under the guidance of Mr. P. Suresh Robuste. These are the contents of this project. Abstract, introduction, existing drawbacks, proposal method, advantages, block diagrams, simulation results, conclusion and reference. The abstract is the main motto of this project is to improve the stability of a DC bus voltage control based on first-order LADRC. LADRC means linear active disturbance rejection control. It is enhanced from the normal PID controllers. The non-linearity, strong coupling, sensitivity to grid voltage swings, and non-linear loads are the features of a grid-connected inverter system for wind power. The upgraded linear active disturbance rejection controller regulates the voltage outer loop to produce the perfect control outcome. First, we design the mathematical model of our LADRC controller. Then we get into the frequency domain response characteristics to analyze the modified LADRC performance with the traditional LADRC controller. Coming to the introduction, this is the schematic of this project. As you observe in the figure, wind turbine is connected to the generator, and basically the function of wind turbine is to convert wind energy into the mechanical energy, and the function of the generator is to convert the mechanical energy into the electrical energy. Here we use the PMSG generator, which is basically permanent magnet synchronous generator, and the output of the generator, that is electrical energy, is given to the rectifier. So the function of the rectifier is to convert the alternating current into the DC current, and the output of this rectifier is given to the inverter. In between the rectifier and inverter, we have the DC bus voltage link. The function of the inverter is to convert that current into the alternating current, and the output of the inverter is given to the grid. In between the grid and inverter, they have placed the filter to filter out the harmonics and or to filter out the harmonics. So why to convert the AC into DC in the rectifier is that we have know that the output of the wind energy is in the form of AC, so which is basically alternating energy. So we haven't controlled the parameters when it is alternate with the time, means it will changes with the time. We haven't controlled the parameters when it changes continuously with the time. So that the thing here is that we want to control, we want to convert that AC, we want to control the parameters so that we want to convert the continuous form into the discrete form. So the rectifier is used here to convert alternating current into the DC current. So after the conversion, we are going to stabilize the voltage at the DC bus link. That is why our project title as Wind Power Inverter DC Bus Voltage Control. By using one of the controller, we have done this. That controller we called as a name LADRC controller, which is Linear Active Disturbance Rejection Controller. This is the basic idea of the project. And coming to the existing system, we have two methods in this existing system. The first one is voltage-oriented control method. What they have done in this voltage-oriented control means only the voltage is controlled in this method. Coming to the direct power control, only the power, that is active or both active and the reactive power, is get controlled in this direct power control method. So the drawbacks of this existing method is may the system cost may the model is get uncertainty, and the major drawback is that the stability of the system is get affected. So these are the two drawbacks of the existing system. So coming to the proposed method. So in this project, basically we have taken main object is to control the DC bus voltage. So for that purpose, we have used one of the controller, which is we call it as a linear active disturbance rejection control. So these controllers replaces the voltage oriented loop control, and it will control both voltage and current in a single loop. That is the basic uh, advantage of this proposed method. So these LADRCs get designed by using the reduced order LISO, that is linear extended state observer. The design of these LADRCs get. So this is a basic block diagram of the proposed method. As you're observing this, we have two loops, outer loop and the inner loop. Outer loop, the voltage is get controlled. In the inner loop, current is get controlled. Normally, in generally, in the existing method, this improved LADRC is replaced by normal PI controllers, normal PID controllers. So by that, we haven't achieved the voltage, uh, uh, desired voltage, and the power factor is not unity, and it is something more than one or else less than one. So by using this improved LADRC controller, we are going to achieve the stability of our system by equating with unity power factor. We are going to achieve the power factor that is equal to 1. So this, in this figure, you are going to observe the two blocks, that is SVPWM and PLN. SVPWM is space vector pulse width modulation. Basically, this is done. Modeling is done by space coordinates, by taking the space coordinates, and PLL is nothing but phase locked loop. This is used to compare the phases from grid and machine side values, and the output of this system is connected to the grid. So what are the advantages of the proposed method is it reduces the noise amplification effect, which is the most important factor, and it improves the LADRC performance. LADRC performance. Coming to the applications, where we use this is mostly we use in power system applications, in wind power plants, etc. So coming to the simulation diagrams. So this project is basically we have divided divided the methods in this project like 3 methods. What will happen if symmetrical drop failure is occurred, asymmetrical drop failure is occurred, and what happened when motor is loading and unloading conditions. So we have made these 3 conditions, and we are comparing these conditions with our LADRC, normal LADRC, and proposed LADRC. As you're observing in this schematic diagram, which we have seen this earlierly in our introduction, that is wind turbine is connected to the machine side controller, that is rectifier we have taken here, controller at the machine side, and inverter is taken at the grid side. So this is the DC bus link. We want to control the voltage over here. So for that purpose, we use the LADRC controller. So coming to the results of our simulation results. So as you observe here, 3A figure. So grid connector point voltage. So the voltage bus bar, voltage waveform of the bus bar under the condition of symmetrical drop failure of 30% of the grid voltage. So 3A figure explains that grid connected point voltage, and 3B figure explains the symmetrical drop bus voltage. So we will observe this in our MATLAB software. We'll see that once. So this is the schematic diagram. So subsystems are there inside these main systems, and we are going to observe the results in the scope 1 and scope 2. So by running, we are going to observe the results on scope. So yes, in the scope 1. So on x-axis we are taking time, and on the y-axis the voltage. Voltage we are going to measure in the system is per unit. So in the symmetrical drop failure, that is we are going in the symmetrical drop failure. Symmetrical drop failure means all the three phases are get affected, or all the voltage in all the three phases is get reduced. That is what we call it as a symmetrical drop failure. If that is taken 30%, if 30% of the symmetrical drop failure is occurred in the system, then how much voltage we are get controlled by using this LADRC. That is our experiment. That is our project. Sorry, that is our project. So as we've seen in the simulation results in the scope 1. So by using the traditional LADRC control, we are going to achieve only 0.973 to 1.021 per unit voltage. So it is not near to the 1, not absolutely 1 actually. It is less than 1 and it is greater than 1. So which is not desirable. So by using the proposed or improved LADRC, we are going to have 0.992 to 1.006 PU. So that is very near to the 1. So the same thing is get followed by the symmetrical drop failure with 40%. And what happens if asymmetrical drop failure occurs? The same way how we have seen for symmetrical drop failure, we are going to see the same thing for asymmetrical drop failure when it is 30%. And we are going to have the results the same way how we are seen for loss for symmetrical drop failure. The same thing we are going to have for asymmetrical. So as you are observing here in this figure, so the voltage waveform of the busbar under the condition of 30%, but it is asymmetrical drop. So there we have observed the symmetrical drop. So what have the Fourier figure explains as the grid connected point voltage, how much of voltage is get stabilized, and 4B figure explains the asymmetrical drop bus voltage. And the last condition is that motor loading and unloading conditions. What happens if suddenly motor is loaded 30% more than the normal one? If unloaded 30%, what happens? So as you've seen in the figure, so the bus voltage of the motor under load and unloading conditions. So motor loading 30%, how much of voltage we have, and how much of voltage is get improved by using this LADRC. And 5B figure expresses the motor load reduction at 30%. So before we have taken the value of 30%. So here we change into the 40. So when the symmetrical drop failure occurs by 40%, then what is the how much of voltage we are going to control. So that is the second case. So we have two cases, 30% and 40%. In that, in under that, we have three conditions: symmetrical drop failure, asymmetrical drop failure, motor loading and unloading conditions. So when motor symmetrical drop failure occurs by 40%, so the power factor is very near to the 1. It is going to uh, uh, achieve one unity power. So by this way, we can replace the traditional LADRC with improved LADRC, and will improve the voltage, and we improve the stability of a DC bus voltage. So the conclusion here is, in order to improve the stability of a DC side bus of the direct drive permanent magnet wind power inverter connected inverter, the traditional LADRC controllers have some disadvantages. So to overcome that, we have improved LADRC. So that uh, controls the DC bus voltage link, and it achieves the unity power factor. And a good control effect we have seen in the improved LADRC where compared to the traditional LADRC. So the simulation results show that the designed voltage outer loop controller greatly improves the voltage response speed and reduces the fluctuation of a DC voltage. So the utilization rate of wind energy is improved, and the control effect is better than the traditional LADC controller. Even when it is distributed by the outside world, the simulation experiment also fully provided the effectiveness of a designed controller. So the improved LADRC controller design in this project provides a new idea for the control of a wind power pre-connected inverters and has a certain engineering application part. Thank you so much.